This module covers dynamics. So the dynamic section will consist of both particle kinematics and rigid body kinematics. So you need to know both. So particle kinematics will have rectilinear motion, curvilinear motion, projectile motion, relative motion. Rigid body is basically what's covered in chapter 16 of the Hibbler dynamics textbook, or all of ENGR 3590 kinematics. So you'll need to know that type of stuff. Linear motion, so force acceleration, angular motion, so torque and angular acceleration. Mass moment of inertia, which is different than the area moment of inertia from statics. Impulse and momentum, both linear and angular. Work, energy, and power. Dynamic friction, so when stuff is moving, and then vibrations. So there is a lot here. Let's take a look at the handbook. So this starts out with just the basic nomenclature of naming variables. And then we have 15 pages of dynamics formulas. So it starts out with kinematics, velocity, acceleration, Cartesian coordinates, basically just split stuff into x, y, z. And then notice here the dot over a variable means a time derivative. So x dot means dx dt, or velocity. X double dot is d squared x dt squared. So that is acceleration. Radial and transverse, so you can have like the UR and the U theta, as we've learned about in class. Here they're called ER and E theta, but it's basically just a unit vector for direction. The rectilinear motion formulas, so constant acceleration, this is used for projectile motion in the y direction, where instead of A, you would have G for gravity. And then curvilinear motion, you can do this in XY coordinates, or you can do this in R theta coordinates. So cylindrical coordinates or polar here versus Cartesian. NTB, not used too much. This is a normal tangential. Relative motion, you definitely need to know. So the relative motion is saying that if you have vector A and vector B, then the relative position between them is this vector that goes from B to A, position of A with respect to B. But then also we have the velocity and the acceleration formulas, where omega is angular velocity, which and then alpha is angular acceleration. So these are all formulas from rigid body kinematics. Now circular motion, this is polar. The main thing to know here is down here, to switch between linear and angular coordinates, you have a factor of r, which is the radius of the curve. So to go from position, so you would have s, which is distance, equals r times theta, which is angle, or v equals r omega, or a equals r alpha. So just know how to switch between linear and angular like that. Normal tangential, not used too much. Constant acceleration equations here. So you can use this, but like mainly you would just use the projectile motion type of equations. So as opposed to using this page, it is generally easier to just use this, where was it? Right here, the particle rectilinear motion. This is the easier one to use. All right, so now back to, okay, projectile motion. Well, here they all are. So talking about the projectile motion is where, since acceleration is only in the y direction, we can decouple the axes and use constant acceleration equations for y, constant velocity equations for x. Now, if you're in a situation where acceleration is not constant, then obviously you have to integrate velocity, integrate acceleration to get velocity, integrate velocity to get position, and don't forget to add your plus constant at the end there and then solve for what the constant value is. So weight is mass times gravity. This is easy with SI units or metric units, not so easy with the imperial or the English units, because there you have to pay attention to pound mass versus pound force. But in most cases, so G, acceleration due to gravity, would be 9.81 meters per second squared, or 32.2 feet per second squared. Now, if you ever do forget that, there is a units section here as far as being able to do conversions. So this is all helpful stuff to know. These are common equivalents, you know, how to convert different things. And then I believe, okay, yes, down here, constants, acceleration due to gravity. So 9.807 or 9.81 meters per second squared metric, 32.174 or 32.2 feet per second squared for English. So if you forget or you're not sure what to use for gravity, then just come look here. Okay, so back down to where we were. Okay, so force. Okay, yeah. So acceleration is force over mass. F equals ma, Newton's second law. Y'all know that. And then for planar problems, so you can either have a tangential acceleration or you can have a radial acceleration. So no centripetal. The centripetal acceleration is v squared over r. Know that. Now work and energy. This one, their variables may be a little bit confusing. So they use T here to mean kinetic energy, and they use V to mean potential energy. Whereas you might have seen these before as KE for kinetic energy, PE for potential energy. It is the same thing. For a particle, you just focus on the translation aspect. For a rigid body, you would have a translation and a rotation in the case that something is translating and rotating both. And then potential energy can be due to gravity, the mgh, or it can be due to a spring, which is the 1/2 ks squared if you're trying to find the energy, or the ks if you're trying to find the force, and you integrate force over distance to get the work. So that's why you would have a 1/2 ks squared for energy stored in a spring. And here it's got that formula for us. Work equals integral of force dotted with distance vector. Now, the nice thing about work and energy is that those are all scalars. So if you have a force, you just do the dot product with the distance, you come out with a scalar value. Impulse and momentum. So the linear momentum F delta T equals M delta V. That is, if you have an impulse, which is a force applied over a time period, it results in a change in velocity. And you can see that this is just Newton's second law rearranged. So we have m times dv dt, which is ma equals f, and then you rearrange, you split up the dv and the dt, and you get f delta t equals m delta v. So angular momentum, they use h, don't know why, but h is what they use. And that is r cross mv, so basically the radius crossed with the linear momentum for circular motion. Or the moment of inertia, and this is mass moment of inertia, times angular velocity. All right, so the impact, you'll need to know E, which is coefficient of restitution, and E is related to how much energy is conserved in a collision. So if E is between 0 and 1, that is an inelastic collision. That is a normal situation. If E equals 1, this is a perfectly elastic collision, which means that all the energy is conserved. And if E equals 0, that's a plastic collision, which means that the objects stick together. So depending on the value of E, the higher E is, then the more energy is conserved, and the lower it is, the more energy is lost. So we can use this formula if you have conservation of momentum, which is here. If there are no external forces, but just the two objects collide, then you have this situation. So mass 1, mass 2, pre-collision speeds and post-collision speeds. Notice that this is a vector equation, okay? So this would be true for x and y, but the impact is only in the x direction, or only along the line of impact. In the y direction, the velocity would be conserved, and that is called the plane of contact. So E only works in the x direction, which here they're calling the normal direction, or the line of impact. So you would use this formula with post-collision speeds for object 2 minus object 1 over object 1 minus object 2. Now friction, F less than or equal to coefficient times normal force. So in this case, you want to see if it overcomes the static force versus the dynamic force. So do your static check. see if the object moves using the static force. If it does move, then switch over to dynamic coefficient of friction, and then you can find the acceleration. Sometimes dynamic friction and kinetic friction are the same thing. So you might see it as mu K or mu D. So motion of a rigid body, we have F equals ma, but we also have some of the moments equals moment of inertia times angular acceleration. And then we have the constant angular acceleration or variable angular acceleration. So these are the same formulas that we learned before when we had A, V, and S, but in this case, they're using alpha, omega, and theta. Okay, so instant center of rotation. This is a point where each one has same velocity at a given instant. This is sometimes covered in dynamics classes, but it's not that common, but it is good stuff to know if, so it's here if you need it. Now, mass moment of inertia, real similar to area moment of inertia, but instead of being integrated over the area, we have distance is integrated over a mass. So I equals the integral of r squared dm. And it says a table listing moment of inertia formulas for standard shapes is at the end of this section. So we will scroll down to the end of this section and just see that real quick. So here we have all the different shapes. So we have this rod rotating, and the rod around its center is here. You can see the little subscript of C. Or a rod around its end has this formula. So two different ones. There's also the hoop, there's the cylinder, there's the hollow cylinder, there's the sphere. And you use parallel axis theorem with all of these if it is rotating around some axis that is a distance away from the center of rotation. Like here, the centroidal axis on this hoop is Z, but the other axis, some distance away, would be the Z prime. So you just figure out, do you want moment of inertia around Z or Z prime? And those are the formulas that you would follow. Now this is for some additional shapes. So we have cone, we have disc, we have hemisphere, we have plate. So just know what your shape is and be able to find the appropriate moment of inertia. So the mass moment of inertia units are kilograms times meters squared, as opposed to the area moment of inertia in statics, which is just a meters to the 4. So we'll go back up here and continue. So radius of gyration is the equivalent radius that we could put a particle at that would have the same moment of inertia as our shape. And then angular impulse of momentum. So this is just the same thing, but like rotational. So vibration, basically, if something vibrates, it bounces back and forth. We know it's going to vibrate if it has a spring. If there's no spring, there will be no vibration. And this C here that they have, this is a damper. So this means that the amplitude of vibration would get smaller. So if it was just a spring, it would bounce one way, other way, one way, other way, just back and forth exactly. If there is a damper, then eventually it will settle out instead of just bouncing forwards and backwards forever. If there's a damper or if there is friction, it will eventually settle out somewhere in the middle and stop bouncing. So we have equations of motion here. So this is basically ma equals negative kx minus c times v plus f. So that's just getting the differential equation for this mass spring damper system, but you can also define the natural frequency and the damping ratio if you want to use this in a controls context. And getting it to get its differential equations, and if you want to actually solve the differential equation, you do it like that. So these plots just show relative amplitude and phase, so depending on a frequency and the natural frequency. So omega here would be like actual frequency or damped natural frequency, and omega n is the natural frequency. So you would have this ratio, and then you would go up to whatever curve is your zeta. And you can see that here, if zeta or damping ratio is super tiny, then you get a big spike. And if zeta is not, then you get no spike at all here if there is zeta equals 1. Okay, torsional vibration. This is not something real common that they would ask you about, but the formulas are here if you need them. So looking at this section, so there are two review videos here. So one on kinematics, so position, velocity, acceleration in the absence of forces. One on kinetics, which includes the forces and torques. And then this playlist here has example problems of all the different types that you might see on the exam. So I would recommend that you try to work the problem yourself and only watch the actual video if you don't remember how to do it. But your cheat sheet for your final exam and any other exam problems that you've had that are short enough to work in like 5 minutes would be good problems to study. There's a practice quiz. You get 2 chances on that. You can, if you want, just take the practice quiz first, see if you score over an 80. If you do, great. You can take the real quiz. If you don't, then you want to go review. Then take the real quiz, and then you can do corrections on it for half credit back. And the next module is strengths of materials.